In this video, we'll talk about coherence pathways in MRI. First of all, let's look at what a coherence is. Suppose you have a population of spins that produces some net magnetization in the transverse plane. If there's any mechanism that generates frequency inhomogeneity across that population, then after some time the magnetization will dephase. After dephasing, the net magnetization can be close to zero, but as a population, the magnetization has a very specific structure, and that structure is not well characterized by the net magnetization. For example, you know that if you apply a 180-degree refocusing pulse to this distribution of magnetization, then the net magnetization will reappear sometime later in the form of a spin echo. The concept of a coherence was developed to provide a compact way to describe such distributions of magnetization and how they react to a series of pulses. This thing here is an example of a transverse coherence. The degree of dephasing of coherence is usually described by a single parameter, and here we'll call it d. D can represent dephasing due to the application of gradient fields, in which case it is the same as k or k-space, or it can represent phase dispersion due to other sources of frequency dispersion such as susceptibility-related field inhomogeneity, imperfect shims, or chemical shift. Okay, so suppose you have a coherence in the transverse plane that has undergone some amount of dephasing d. A transverse coherence is typically labeled F, so we have F sub d. Now let's look at what happens to the coherence when we apply an RF pulse of flip angle alpha along the x-axis to this coherence, which rotates our pancake of magnetization about the x-axis. And we'll look at the transverse and longitudinal components of the resulting distribution separately. Looking at the transverse component first, we see that the transverse component of the coherence will in general have an elliptical distribution, though this ellipse could be collapsed into a line if alpha equals 90, or return to a circle if alpha equals 0 or 180 degrees. Now it turns out that this elliptical distribution can be described exactly as the sum of two counter-rotating coherences, and that these are simply f sub d and f sub minus d, weighted by two coefficients which we will call a and b. We can write down equations that allow us to solve for a and b by inspection. Now f sub minus d is equal to f sub d reflected about the x-axis, or in other words, f sub minus d is the complex conjugate of f sub d. Therefore, along the x or real axis, f sub d and f sub minus d are identical. Now looking at our elliptical distribution, we see that the distribution along the x-axis is unchanged by the RF pulse, since that was the axis of rotation. Therefore, we can write down that a plus b must equal 1. On the y or imaginary axis, the component of f sub d and f sub minus d have opposite sign. Since we see that the ellipse has dimensions cosine alpha in the y direction, we can write down that a minus b has to equal cosine alpha. So now we have two equations and two unknowns, and we find that a equals cosine squared of alpha over 2, and b equals sine squared of alpha over 2. So the RF pulse splits f sub d into two coherences, an unchanged coherence with coefficient a, and a phase-inverted coherence f sub minus d with coefficient b. These components are sometimes referred to as the transparent and spin echo parts of the RF pulse, respectively. Okay, so now let's take a look at the longitudinal component of the original coherence after the RF pulse. This is a one-dimensional distribution along z, and if you think about it, you can see that this distribution looks like the y component of 1/2 f sub d minus f sub minus d, but rotated to the z-axis. And in fact, that's what it is. The x component of f sub d minus f sub minus d is 0. These longitudinal coherences are labeled z sub d, where the subscript refers to the degree of dephasing in the transverse plane that occurred prior to rotation into the z-axis. One of the reasons that z is defined this way is that when it is tipped back into the transverse plane, it in fact does reproduce the combination of transverse coherences 1/2 f sub d minus f sub minus d. The coefficient for this longitudinal component is simply sine of alpha, since that is the coefficient for the rotation of y magnetization to z magnetization. Okay, so now let's write down a complete expression for the transformations performed by an RF pulse on coherences. As we have seen, f sub d is transformed into an identical transparent component, a spin echo component, and a longitudinal component. The additional phase terms in front account for RF pulses that are applied at a phase angle phi relative to the x-axis. F sub minus d gets transformed into similar components, and z is transformed back and forth to f with coefficient sine alpha and to itself with coefficient cosine alpha. Note that this expression does not hold for d equals 0, only for non-zero d. d equals 0 corresponds to net magnetization, and the response of magnetization vectors to an RF pulse is a conventional rotation matrix. Now the point of connection between coherences and magnetization is that f sub 0 is transverse magnetization, and that's the only point of connection. It's also important to note that both net magnetization and coherences can coexist. So in addition to these transformation matrices, there's a graphical way to look at coherences and coherence pathways that make some pulse sequences easier to understand. On this axis we have time, and on this axis we have the degree of dephasing d. If we have equilibrium magnetization and apply a pulse at time 0, then we can generate some transverse magnetization m sub xy, which also equals f0. If there's a constant source of frequency inhomogeneity, then this f0 will over time dephase and drift to f sub d, where d is not 0. Now let's suppose that a second RF pulse is applied here in time, and for convenience, call this amount of dephasing 1. And this point is f sub 1. When we apply a second RF pulse, our transformation matrix tells us that our coherence is transformed by this pulse to f sub 1, f sub minus 1, and z sub 1, with the weights given in the matrix. In addition, any longitudinal magnetization that exists at this point in time will be partially converted into new transverse magnetization, and therefore a new f0. We then have transverse coherences at d equals 1, 0, and minus 1, and these all shift up 1 in d over the next time period. We also have a z1 coherence, which does not change in degree of dephasing since this magnetization is longitudinal and is therefore not subject to phase dispersion. This is typically represented by a dotted horizontal line. The family of coherences in general then divides and propagates at each RF pulse with coefficients that you can calculate and follow. Anytime a transverse coherence passes through d equals 0, net transverse magnetization is generated and an echo is formed. So let's look at two commonly used pathways on this diagram. This pathway is the basic spin echo pathway and uses one pulse to generate transverse magnetization and a second pulse to bring the coherence back to f0. You will note that if the pulses are 90 degrees and 180 degrees, the weighting of this pathway is 1, and no other pathways are generated. But this approach also allows you to calculate the magnitude of the spin echo for any combination of flip angles. Another pathway that is commonly used is called the stimulated echo, and it follows this trajectory, forming an echo here. Note that during this middle period, the coherence is longitudinal, while all other pathways are transverse. And this provides an opportunity to filter out only the pathway you want. If you apply a large Crusher gradient pulse during this period, then all transverse coherences will be dephased, but the stimulated echo pathway will be unaffected and will be the only signal that appears. Finally, let's take a look at the effect of T1 and T2 relaxation on these coherence pathways. Transverse coherences, like transverse magnetization, always decay towards 0 in the absence of RF pulses. So between any two RF pulses with time spacing t, any f sub n, including f sub 0, or transverse magnetization, will progress to f sub n plus d times e to the minus t over t2, where d is the incremental dephasing associated with this time interval. Longitudinal coherences decay towards 0 with time constant t1, but longitudinal magnetization decays towards the equilibrium magnetization m sub 0. So we have that z sub n goes to z sub n times e to the minus t over t1, for n not equal to 0, and mz decays towards m0. So the use of coherence pathways provides a framework for the analysis of many pulse sequences and is particularly helpful for understanding spin echoes, stimulated echoes, fast spin echoes, and both spoiled and unspoiled steady-state gradient echo sequences.